dây HDMI hay là dây VGA. Dây VGA là đang mở hơn HDMI.
Em áo giả cho nó đẹp.
Bánh 5, 16, 17, 18, 19. Tập 20 người. 20 người.
Okay, so good morning everyone. We have to go because today is quite important lecture, and I think that we should go faster to finalize the lecture before that. And after that, we will have another lecture talking about the chemical solution. That's quite simple because it's quite like you already study in high school. So I will say that in general chemistry 1, the class discussion about the hybridization of orbital and the molecular orbital is the central one. Okay, so that's why I cannot wait for other. Even I know that today, this week will be the last week, and for the tutorial class, they know check attendance list, right? They know checking of attendance. And in the group of lecturers, we understand that more of you will not come to the tutorial. It's up to you, it's your option, because the question for the final test will come from either the main lecture or from the tutorial. Is corresponding to 80% of the total question, you know, right? So if you don't want to come, it's okay. We respect, no problem. You see that normally this class have 300 students, more than 300, and we have now about 30, okay, 10%. Excellent, professional. To be honest, we cannot go far with these activities. We cannot go far. If you think that you can do a good job after graduation with this kind of professionalism, I would say that it will be too big. Anyway, so we talk about the hybrid orbital. Why we talk about hybrid orbital? Because remember that the experimentation, what we observe is the real one. Okay? What you explain by different theory is not the nature, but your understanding, the human understanding about the nature. It means that you observe something, you try to formulate a hypothesis, a theory, to explain what you observe. And then, sometime later, people will observe something different. Your theory will be no longer correct. So you need to extend your theory, develop your theory. So the hybrid orbital is something like this. For example, in the previous class, we talked about the bonding by overlapping of two orbitals, right? So take the molecule of C84, molecule methane, C84, right? It will have what you observe experimentally. In the molecule C84, you have 4 identical bonds between carbon and hydrogen. You have 4 hydrogen in the C84. You cannot distinguish which one and the other one. All 4 hydrogen will be the same. Okay? It's also observable that all the bonding between carbon and hydrogen will have the same length. Okay? And all the angle between hydrogen, carbon, hydrogen will be similar. Okay? That's what you observe. However, when you learn about the bonding theory by the overlapping of two orbitals, you understand that carbon have 4 valence electrons, right? Inside, you have an electron configuration. You draw like 1s2, 2s2, 2p2, right? Is it correct? So now you have, in the valence orbital, you have 4 electrons. You have 2 electrons in the orbital s and 2 electrons in the orbital p. Okay? So now if you want to bond 4 valence electrons by overlapping with 4 hydrogen, you should use 1 orbital s and 3 orbital b. But in 1 orbital s, you have 2 electrons. In 2 orbital b, you have 1 electron, and 1 orbital b, you have no electron. So, if you just base on the overlapping of the orbital, you can understand that 4 hydrogen will be not identical. Because 1 hydrogen will come from the overlapping of the orbital 2s of the carbon and orbital 1s of hydrogen, right? 2 other carbon hydrogen will come from overlapping of the 1s of hydrogen and 2p of carbon. Okay? And the third one will be 1s of hydrogen with the empty p of the carbon. So that means in the 4 bonding, in the 4 carbon hydrogen, you will have at least 3 different types of bond, right? You have a SS, SP with 1 electron and SP with 0 electron. So that means what you understand is not correct. Is it correct? Because what you observe is that 4 hydrogen are absolutely identical. 4 carbon hydrogen are exactly identical. But what you explain are not identical. So you have to find a way to explain again to say that actually they are identical. You understand the problem? So to explain why the 4 carbon hydrogen are identical, you have to use the concept of hybrid orbital. Hybrid, that means you take A and B, you mix together, and there's no reaction. The product of these hybrids will have both character of the A and B. Okay? So, that's the concept. So, take one case. Like, if you take the barium, you have 2 valence electrons here. Okay? Now, if you want to make the bonding with the fluorides, you can say that the compound BeF2 exists, that experimentally you observe, right? And in this compound, this angle is 180 degrees. And 2 bond barium fluoride will be identical. That you observe. The same like the case of CH4. If you take only the orbital S here, basically you can overlap with the orbital P of the fluoride. So like this one, S a barium and P a fluoride. And in that case, you will have one orbital Sp by this bonding. Okay? And the second orbital will be the orbital P here, empty, and the orbital P of the fluoride. So you will see that the two barium fluoride will be not identical. So, same for the CH4, how can we explain to make them identical? Because remember that the identical bond as what you observe, not you imagine. What you explain here by the overlapping orbital is your understanding. So you need to adapt your understanding to progress. Okay? So how we can do? We say that inside the two, in the orbital, you have two electrons. So one electron will be excited to move to the orbital P. Okay? So now you have two orbital X with one single unpaired electron. And then the two orbitals will be mixed together to generate what we call hybrid orbital. By the linear addition, you have one orbital S plus one orbital P. So you mix together, it will generate two orbital Sp. Sp means it contains both the character of orbital S and character of the orbital P. So how we can say they contain both characters? For example, the orbital S will be sphere, right? And the orbital P is like this. Now you mix together, you have two domains. The orbital hybrids, Sp, will have two domains. It looks like the orbital P, right? It has two domains, that means the character of the orbital P. However, there one domain is look much bigger, much sphere. So you can say that this domain have character of orbital S. Okay? So we say that in terms of the set, in terms of distribution of electron, the orbital Sp have both character of orbital S and orbital P. Okay? You can say that it will have 50% character of S and 50% of character of P. The same if you take one S and two P, the hybrid orbital still have both character S and P, but it will have more character P than character S. Okay? You can say that in the case of Sp2, you have 30%, 33% of S and 66% of P. So, by this way. Okay? Of course, if you put the two orbital Sp together in the same X, you will have the total orbital, which is the mixing of the S and P. So it's cover the character of the orbital P, as I mentioned. So it looks like this. Okay? Hybrid orbital is look like this. We mix, but X will retain the character of the original orbital. Okay? Easy to understand, right?
Yes.
So now, when you have two orbital Sp already a barium, X will have one single electron, so each will overlap with orbital P of the fluoride to make two identical bonding. Okay? Because two orbital Sp are exactly identical, so when you overlap with orbital P of the fluoride, it will generate two identical bonds. So you see that by mixing the orbital, by providing a new theory of mixing orbital, you can now explain what you observe in the experimentation. Okay? So ladies and gentlemen, the future scientists, you should remember that what you observe is the nature. But what you understand comes from your mind. Okay? Maybe you are not able to understand all, but what you need to report, you report the correct observation you observe. Don't try to observe what you want. Observe what you can and explain what you can. You get what I mean? Đừng chỉ nhìn những cái mình muốn nhìn. Yeah? Okay. So here are three cases of hybrid orbital. You have S and P, So you have one orbital S, one orbital B. So in this case, the hybrid orbital, you can say that contain 50% character of S, 50% character B, and so on. You see, easy. Now, what is important is in terms of energy. So orbital S have lower energy than orbital B. But when you mix together, it's like you take the average. Okay? So the hybrid orbital will have energy somewhere in between the S and B. Okay? Because here, take note, remember, later we talk about the molecular orbital. When you consider the bonding, you need to consider two things. First, about the energy. Okay? The energy of orbital. If one orbital is here and one orbital over there, they cannot make a bond. But if you have the same energy, the second question you should ask is about the shape, the geometry of the orbital. Let's say you have two orbital B, they are the same energy, they are in same direction like this, the overlap will be possible. You have two orbital B of the same energy like this, possible. But if you have one orbital B like this and one orbital B like this, there's no way. Okay? So it means that you need to consider about the energy and the geometry and the orientation of the orbital. Okay? Okay, so here for example you have the sp2, 1s, 2p. So in total you have 3 sp2, and if they will arrange in the planar like this with the angle of 120. Okay? sp4 you will have like this with the theta hero orientation, and then you have the angle of 110 degrees. So now, in practice, how can you predict the hybrid orbital, whether sp, sp2, sp3, sp3d2, for example? First, you have to draw the Lewis structure of the molecule or ion. Second, you determine the electron domain geometry using the V for valence, S for valence shell electron pair repulsion. Okay? And then you specify hybrid orbital for the bonding electron pair based on the geometry. For example, first you take Na3, you draw the Lewis structure, right? How to draw the Lewis structure, you need to practice. I will not remind, okay? Then you have 1 domain, 2 domain, 3 domain, and 4 domain. 4 domain arrangement will be pyramid, right? Theta hero. And then you have this electron domain geometry. So to make this electron geometry, you have 1, 2, 3, 4, and this is the theta hero. So the hybridization should be sp3. For example, this one. Okay? So to come to specify whether it's sp2, sp3, you need to know about the geometry of the fractal. Okay? So you see now that all link together. Okay? First, identify the Lewis structure. Second, make the geometry of molecule, and then you can predict the hybridization of the orbital that make this geometry possible. Okay? So here you have hybrid orbital geometry. You have sp linear, sp2 that will be trigonal planar, sp3 it will be theta hero. And if you have S from the third layer, you have sp3d, right? You can, because now the valence electron can look like in the S and P and D, right? So you can mix 1S, 3B, 1D, so you have sp3d, so you have this trigonal pi pyramidal. So if you can identify one compound with this geometry, you could be able to predict what will be the hybrid, which is sp3d. Okay? So if you have sp3d2, that means you could expect the octahedral like this. Okay, so you see all linked together. For sure, in this series, if you are not able to calculate the number of valence electron, you are not able to draw the Lewis structure. If you are not able to draw the Lewis structure, you are not able to predict the geometry of molecule. If you are not able to predict the geometry of molecule, you are not able to predict the hybridization of the orbital. Right? So all linked together if you want. Now, just we talk about the single bond. How about the multiple bond? So, here are the definition. A sigma bond is a bond in which shared electron density is concentrated directly along with the internuclear axis between two nuclei involved in the bonding. Okay? It means if you have two atoms to make a single sigma bond. Okay? So the electron density will be concentrated in between the two nuclei. That's the meaning. So you see that you have the electron density will concentrate in between the two nuclei. Okay? In the case they have the same electronegativity, you can expect that electron density will stand in the middle between the two nuclei. It says that the electron density in the hydrogen on the left side and on the hydrogen on the right side will be equal. So that's why there are no bond dipole. There's no polarity. Okay? So here is orbital S and orbital S, and you can have also the same sigma bond with the orbital P and D. So here you have orbital P and another orbital P. They overlap by this way, hit to hit like this, so you have sigma. So it also means that you can have the same orbital, the same sigma bonding between the orbital S and orbital B. One orbital S overlap with one orbital B, you can make one sigma bond as well. One orbital S and one orbital D, you can make also one sigma bond. Okay? So the sigma bond is a single bond where the electron density will not lie in between the two nuclei. For the P bond, from the sideway overlap is that means you have this orbital and this orbital, they overlap like this way. Just by the sideway. Heat way is like this. Okay? So by the sideway overlap of the p orbital resulting in the region of the electron density that are concentrated above or below the plane of the molecule. That means here you have the internuclear axis. That means the line connects between two nuclei. You can see that the electron density, due to the overlapping of two orbitals, by the sideway overlapping, the electron density will be above the bond or below the bond. Okay? While for the sigma, the electron density will be in between two nuclei exactly on the same axis of the bond. But for the p bond, you will have electron density above and below the bond. For example, this one is quite clear, right? You have above electron density, higher, lower, you have also higher electron density. But in the internuclear axis, that means the line connects to nuclear, the electron density is low. Okay? So that's the difference compared with the sigma electron. So you can, by this understanding, you can expect also the overlapping, that means the p bond between the p orbital and d orbital, right? Is it correct? Because the d orbital is like this. So you have a p orbital, so you have a sideway. Can you imagine this? Okay, here. So you have p orbital and d, so here you have sideway overlapping. The electron density will be above or below the internuclear axis. So here you have p, d, p bond. Okay? So here you have pp, pd, and you have also dd. So if you have two d orbital on the two atoms, you can generate also the p bond. Okay? So when you take a look, wait, easy one. When you take a look about the strength of this bonding, you can understand that if you have a pp bonding, so the distance, the overlap will be larger and the distance between two nuclei will be shorter compared with the pd. and shorter with the DD. For 2 orbital D, the overlap path will be very low. So it says that if you have a P bonding between a PP, PD, and DD, the P bond between PP will be stronger than the PD, and the P bond due to the overlap of DD orbital will be weak. So that's why when you want to break the orbital B of the bonding B, and this bonding B is due to the overlap of 2 orbital D, it's quite easy. You don't need to pay too much energy. Okay? So when you have a multiple bond, that means all the time you will have one single bond, which is sigma bond. And then you can have double bond, it consists of one sigma bond and one P bond. If you have triple bond, you can have one sigma. All the time you should have one sigma bond, right? Because that you can understand like this is reason to be of the bonding. If you don't have a sigma bond, it's going to be not possible to have double bond. Okay? So for the triple bond, you have one sigma and 2 P. So for example, if you look at the double bond in the molecule, famous molecule C2H4, you will see that first you should know about the geometry of this compound, right? And when you know the geometry of this compound, you see that you have 1 domain, 2 domain, and 3 domain. And it will be trigonal planar. So when it's trigonal planar, that means you will have the hybrid orbital sp2. So to generate sp2, you can imagine as following. Normally, in the ground state, in the normal state, electron will be N2 and P2, right? So to prepare the sp2 hybrid orbital, one electron from S should excite to the orbital B, okay? And then you will have the mix of 1s and 2b to have 3 orbital sp, and it also means that you have one orbital B will be not like the other hybrid orbital. Okay? The first one will be different compared with the 3 other one. So 3 sp orbital will bond 1, 2, and 3 sigma bond with 3 other atoms, 2 hydrogen and 1 carbon. The remaining orbital here, like this, will overlap with another orbital B by the sideway overlapping, so you have p orbital. Okay, so that's the way you construct the multiple bond. First, you build the sigma bond. To build the sigma bond, you should be able to predict the hybrid orbital. To predict the hybrid orbital, you should be able to predict the geometry of molecule. Okay. So if you look in terms of electron density, you will see that the p bond here, the electron density will look like above the bond, carbon-carbon, and below the carbon-carbon bond. So it means that now if you put this compound in the chemical reaction, if you have this compound, because of electron density above and below, it can behave like a base, a language base if you want. So now another agent which have lower electron density, like for example H+, okay, the proton, and it would be able to attack from the top side down or the bottom up. But it will be very hard to attack from the sideway, right? Now if you put H+ in the reaction with this one, the H+ will be first attack from this direction, but not this direction, nor this one. Because the electron density by this direction and this direction will be low. You get what I mean? Is it clear? So we understand the electron distribution to help us to predict the chemical reaction following. Chỗ này có hiểu không? Bây giờ nhá, thầy nói là cái orbital pi, cái liên kết pi ấy, thì cái mật độ electron, tại vì cái liên kết pi là do cái sự san phủ cạnh, san phủ bên của hai orbital đúng không? Thế thì cái phần mà sen phủ là cái phần có nhiều electron nhất, đúng không? Thì nó sẽ nằm ở bên trên hoặc nằm ở bên dưới so với cái liên kết đây. Trong khi đó cái liên kết sigma thì nó do sự xuyên phủ giữa hai đầu của orbital, thì cái mật độ electron nó sẽ nằm giữa và nằm trên cái liên kết carbon carbon, đúng không? Đồng ý không? Chỗ đấy hiểu chưa? Thì như ở cái hình vẽ này rất là dễ hiểu, cái liên kết carbon carbon thì cái sigma bond ấy, thì cái electron nó sẽ nằm giữa hai cái hạt nhân carbon carbon, đúng không? Thế nhưng mà với cái liên kết pi thì cái mật độ electron nó sẽ nằm cao ở phía trên và phía dưới, còn ở giữa hai cái carbon carbon này thì không có. Đồng ý không? Hiểu theo nghĩa là nếu mà cả cái phân tử này mà các em nhìn như thế này thì sẽ thấy là phía trên của cái liên kết carbon carbon và phía dưới cái mật độ electron rất là cao. Đồng ý không? Ok, đến chỗ này là ok đúng không? Thế khi mà có mật độ electron cao như thế thì bởi định nghĩa acid base em có thể consider cái chất này nó như là một cái base Lewis, đúng không? Đồng ý không? Base Lewis acid là chất có thể nhận electron. Lewis base là một cái base có thể cho electron, đúng không? Thì những cái nào mà có hai electron density thì có thể behave như là một cái Lewis base. Ok. Thế bây giờ trong cái acid base có một cái base, thì nếu như em đưa một cái acid vào thì nó sẽ có phản ứng acid base, đúng không? Giả sử như bây giờ em đưa vào cái hệ này một cái H cộng, thì cái H cộng nó sẽ tấn công vào chỗ nào? Nó có mấy hướng để tấn công, đúng không? Một hướng từ bên trên xuống, một hướng từ bên dưới lên, một cái từ bên cạnh thế này, một cái bên cạnh kia, đúng không? Đúng chưa? Thế thì cái H cộng là cái nó không có electron, nó là acid, thì nó sẽ tấn công theo cái chỗ nào ấy mà cái mật độ electron nó cao nhất. Đúng không? Thế thì nó sẽ không tấn công từ bên phía tay trái sang hoặc là từ bên phía tay phải vào, tại vì mật độ electron ở phía này rất là thấp, thì nó sẽ prefer là tấn công từ bên trên xuống hoặc từ bên dưới lên. Đúng chưa? Đúng không? Thế nó tạo ra cái hệ lụy là gì? Nếu mà cái H cộng mà nó tấn công từ bên trên xuống, giả sử cái H cộng nó đến ở chỗ này, đúng không? Thì về mặt nguyên tắc thì cả cái orbital này, cả cái orbital hai cái orbital B này bây giờ nó đã được sen phủ, kiểu theo nghĩa nó thuộc cả hai ông, chả thuộc vào ông carbon bên trái, chả thuộc carbon bên phải, đúng không? Đúng chưa? Thế nếu như bây giờ cái H cộng đi vào chỗ này, nó phản ứng, nó sử dụng cái electron của cái liên kết pi đấy, thì hiểu theo nghĩa là carbon hydro từ H cộng ấy, ở chỗ này, và cái carbon này nó sẽ tạo thành một cái tam giác cân. Đúng chưa? Đúng chưa? Và như thế thì nó có thể tạo thành hai chất tương đương nhau. Sau khi mà nó tạo thành tam giác cân rồi thì liên kết nó phải cắt ra, tại vì là hydro nó chỉ tạo được một single liên kết thôi, đúng không? Nó không thể nào liên kết cùng một lúc với cả hai carbon được, đúng không? Thế thì bây giờ nếu mà nó cắt ở phía này thì nó sẽ thành carbon hydro ở chỗ này, đúng không? Và nếu cắt ở bên này thì nó sẽ thành carbon hydro ở bên này, đúng không? Kiểu theo nghĩa là cùng một lúc em sẽ được hai cái đồng phân, hai cái chất với cái xác suất giống nhau. Đúng chưa? Còn nếu như mà cái hydro mà đi từ phía này hoặc là hydro nó đi từ phía này, thì nếu mà nó đi từ phía này thì nó chỉ được một đồng phân thôi, chỉ được với một cái carbon này thôi, đúng không? Còn nó đi từ phía kia nó chỉ được với một carbon kia thôi. Hiểu chưa? Thế thì vì cái chuyện như thế cho nên là trong hóa học hữu cơ sau này ấy, các em có thể hiểu được cái mechanism của nó, là nó sẽ tạo ra bao nhiêu đồng phân, nó tấn công như thế nào, nó liên kết ở chỗ nào. Đồng ý không? Nhé. Tất nhiên là nó còn câu chuyện sau nữa, tí thầy nói sau. So, for the triple bond, first you have this compound, you should identify the geometry. The geometry will be linear, okay? So you will have one sigma and two p bond. So the hybridization of the carbon will be sp, one s and one p. The number of electron domain will be 2. So the hybridization sp. So to make it, you have one s and one p. You have two orbital sp and you have two orbital with unpaired electron p. Okay. So first you have two orbital sp. It will bond with two orbital s of the hydrogen to make a 2 sigma bond. Okay. And then you will have two orbital p say will overlap by the sideway overlapping. So you have the first double bond and the second double bond. Okay. So in the case you have a resonance structure like the benzene, you could be able to do the same thing. So let's say if you look at the benzene, you know that the angle here, carbon angle 120. So you are able to predict again the hybrid orbital will be sp2. So you do the same thing. You have 1s, 2p. So you have 3 orbital sp. One will bond with this carbon, one will bond with this carbon, and one bond with the hydrogen. Okay. So 3 sp2 will be one bond, and one bond. You have the angle 120 between, right? So it remains one orbital b, which is perpendicular with the molecular plane, like this one. So imagine that you have, so here you have the molecule C6, okay? So each carbon will stand on the same plane. So you have orbital B, which is perpendicular like this, okay? So this orbital and this orbital and this orbital, they will overlap. So all of the, you can see that 6 p orbital from the 6 carbon, one like this, so all the perpendicular with the molecule, right? So you can imagine they will overlap this one, and this one. So you have 3 p bonding, right? But you can do the same thing, but in the inverse direction. This one, and this one. So you have 3 other p bond. So actually, that's exactly the concept of the resonance structure that you learn. Okay? So in reality, all of these 6 orbitals will overlap. So it will create a cloud of electrons above the molecule and below molecule. So here you are. You have the first domain, first way of making the p bonding, the second way. But actually the real is that all of the 6 p orbital will overlap. So you have one domain above and one domain below high electron density. Okay? So you know this guy, right? You know this scientist, Kekulé. No, you don't know. So he was the first scientist who proposed the structure of the benzene. Because at that time they know that there are one compound with the formula C6H6. 6 carbon, 6 hydrogen. But nobody knows how 6 carbon can bond together with 6 hydrogen. Okay? There's no concept of hybridization, there's no concept of orbital at that time. They just know 6 carbon and 6 hydrogen. And 6 carbon behave identically by the same way. So how you can draw on the paper the compound by the C6H6 like this. So Kekulé proposed this kind of structure with 6 carbon run around to make one circle like this. And of course people invent whether Kekulé is set or not, we don't know. But people invent to say that one day Kekulé is working very hard and feel tired. He fell asleep, and during sleeping he dreamed about one snake like this. Huh? So that is something I don't really believe, but it's written in the book, so we refer. So for the resonance structure of NH3, for example, you see that you have if by this way you can have one double bond here and 2 single bond by this way, right? But actually you have this hybridization, overlap of all the orbital B. So basically all of the 3 structures are identical. So that's the concept of resonance structure, again, we have learned. So here is the important. If you take any pencil, okay, in the pencil you have graphite. And in the graphite you have a lot of the layer which is graphene. Okay? And you see that each graphene, you have a several C6 cycle like this, right? So you see that X unit is one benzene. But if you take benzene in the 2 dimensions, you multiply, you have this graphene. And you know that in the graphene, in one only graphene, you have very high electron density above and below. So now if you use the same concept, you will see that there's a lot of, because all the orbital B will be perpendicular with the benzene, graphene, so you have a lot of electron density above and below the graphene sheet, right? Now, what I mean by this? When you have an electron overlap between the orbital B of this atom, and this atom, that's what I mean. It means that there is electronic communication between this atom and this atom. The atom number 1 and the atom number 4 here. They can talk together, they can communicate. Okay? So what I mean, if I inject electron from this point, I inject electron to here, the electron will quickly delocalize to come this electron to this atom. Okay? Is it correct? So the fact that you can delocalize, you can make the electron move is electrical conductivity. Right? You put electron in the metal, it have excellent conductivity because the electron will escape from the other side of the metal. So the same for the benzene here. You put electron here, the electron will quickly move to this atom. Okay? So now, you imagine that you take graphene, you put the electron at this atom, this one, very quickly the electron will move to the here. Okay? So that makes graphene is one of the best conducting material, even better than copper, better than gold. Okay? How you can understand like this? How can I understand the concept of overlapping? We call the conjugated. Now if I touch the guy, this guy will not feel anything. Okay? I do like this. This guy will not feel anything. I don't care. Okay? If I do like this guy should feel nothing. Okay? But now if you put hand this guy will come. Okay, you see? So that's the concept of conjugated. Okay? If you don't communicate, you don't overlap, take hand in hand, you behave like individual atoms. So I inject electron in you, you don't feel anything, you feel. But the guy this high will not feel anything. But if you all of you take hand in hand, I fell, the guy over there, he did not pay attention, he will fail. Okay? So that is the concept of conjugated. That also the concept of thermal heat energy conducting and the electrical conducting. Okay? You understand it, right? Okay. Now, you have graphene. It's a very good conductivity. Excellent. But you have to apply in some device, like electrical device. And it's a solid. Okay? So to put an electrical device by a solid way, you cannot do. So what you have to do, you disperse in solvent, and then you drop on the device, and then you have a device. You got what I mean? Now, for example, here is graphene, right? Yes. It's good conductivity. But I want to make the connection, the electrical connection between this side and this side. Okay? I should drop one graphene, another graphene, so to make the connection happen, right? But this is solid. I cannot take hand to put one by one. It's at angstrom side or nano side. I cannot manipulate with my hand. Okay? What I can do, I will take this solid, I disperse in the solvent. Okay? I will drop in my solvent. Okay? I disperse it, I make a solution. Is it correct? When I have a solution already, I will make like this. Okay? And then later on, the solvent will evaporate. I have a solid connection. You understand? Okay? But now, that's the idea. But now you have a problem. What is that? This one, you will see whether it's polar or non-polar. It's non-polar, right? So if you want to dissolve it, you have to find the solvent which is non-polar. For example, benzene. If you put in benzene, it will be excellent. However, in industry now, you are not allowed to use benzene because it's cancerous. If you expose to benzene for a long time, you probably have a chance to get cancer. So in industry, they cancel all the using of the benzene. So it's better, the best solvent you can use will be water, right? Because I drink water every day. So if I use water in industry, it will be perfect, right? But the problem is that benzene is non-polar. Water is polar. So graphene cannot be able to dissolve in water. My question is, how can we make graphene more soluble in water? That's the question that can make money, not only to get 20/20 in general chemistry class. Okay? So how can we make graphene from not soluble in water to be more soluble in water so I can manipulate with water solvent? That is my question. How can we do? Any idea? Yes?
We can break it down into smaller pieces.
Okay, good idea. Yes, you can break it down into smaller pieces. However, when you decrease in the domain, in the size, you have a smaller size, what do you mean? If all of you are a big graphene, okay, and hand in hand, I take this guy, the guy over there will fall, right? But now he proposed that, okay, we break in a small domain. That means this will make a group. All of you will be hand in hand. Another guy will make a group hand in hand. So in between there is no connection. Okay? So that means I insert electron here. This guy will fill, but the guy over there will fill up. So it means that when you break in a smaller domain, the conductivity will decrease. So you increase the solubility, but you decrease the conductivity. Okay? So what could be the other solution? Yes, people think like that. So there is a big guy in Rice University, Chem January, who was the original of this idea. I break everything. I break a big graphite to become smaller graphite, and to become smaller graphene. And he can increase the solubility. He can make a solution of graphene in water stable for few years. Okay? However, the conductivity is good. So, James, sorry, that's for fun. So, what could be the other solution? Yes, but breaking the big one to smaller one is very good original idea. But if you want excellent conductivity, then it's not good. How can we do? Think about this. How can we do? Yeah, please.
So we pump more oxygen in it and adjust the temperature and the pressure to make hydrogen peroxide.
Hydrogen peroxide?
It's non-polar.
Hydrogen peroxide is non-polar? A2O2, right? You mean A2O2 is polar? First, you have the solution of A2O2 in water, right? So it means that A2O2 is soluble in water. Okay? So it's soluble in water, that means it's polar. And the second thing, I will show you. The molecule H2O2 is O, H, like this, right? Okay? This one is non-polar. Okay? So you have this. Okay? So what would be the total vector of this gamma? Huh? Very interesting. Thank you. Where the total vector of A2O2 is different than 0 or 0. Zero or not zero? Zero, right? So why this can be soluble in water? Huh? Được. Tốt. Được không? Hả? Tốt. Why? This very nice. So actually, have you heard about the hydrogen bond? Right? So if you put the molecule water here, you will have this chemical, right? Is it? And then here you can have also like this one. Okay? So we will say that the molecule H2O2, even the polarity is 0, the non-polar. However, this can be solvated by water. Solvated, water like solvent. So if you have one candle surrounded by the solvent, we call the solvated. Okay? Okay? So if you have one molecule A and you have a molecule solvent around like this, okay? So we call the process is solvatation. Okay? And the species we call the solvent species. So because of this process, H2O2 can be soluble in water. Is it clear? Now, back to the question of graphene. How can we make graphene better soluble in water? You can try to make this graphene solvated. Okay? So in principle, if you are basing on the polarity, graphene is non-polar. Water is polar. So if you want to make graphene soluble in water, you have to make either changing the polarity of graphene to introduce higher polarity, or you should reduce the polarity of water by introduce one compound which is soluble in water but lower polarity. You get what I mean? For example, if you talk about water and ethanol, C2H5OH and H2O, which one have higher polarity? Water, right? water will have higher polarity than ethanol. So now if you take solution of water, you put 50% of ethanol inside. That means the polarity of this 50% ethanol solution will be lower than water. Is it correct? Có đúng không? So now if you take another alcohol, for example, isopropanol. Okay? Isopropanol, C3H7OH. And you put in the water, of course the polarity will decrease. So we say that if you want, you can try to put isopropanol or isobutanol in the water to increase the solubility of graphene. Okay? Is it correct? Now, that you change the polarity of the water. Can we change the polarity of the graphene? Can you make it more polar? Yes, you can oxidize it. For example, here, this carbon, you can oxidize to make COOH, for example. So if you make this one, COOH, all of the carbon in the around becomes COOH, you can increase drastically the polarity of the system. Next question. How can we oxidize graphite and graphene? We want to oxidize, but how can we do it? What could be the chemical reaction? Cái chất oxy hóa mạnh nhất mà các em biết là gì? Hả? Các thanh niên vừa mới thi đại học xong đúng không?
Oxide mạnh nhất.
Chất gì? Chất oxy hóa mạnh nhất mà các em biết là gì?
Oxy.
Hả? Vàng á? Ông bị ngáo à? Vàng làm sao mà oxy hóa được?
Oxy hóa, chất oxy hóa mạnh.
Nó là chất oxy hóa không phải là bit oxy hóa. Okay. Chất oxy hóa lớn nhất, mạnh nhất mà các em biết là gì?
Oxy.
Hả?
Natri.
Chất oxy.
Natri nó là một trong những chất khử mạnh nhất. Chất oxy hóa mạnh nhất mà các em biết là gì? Clo.
Nhận.
Vàng. Cái quái nào mà các ông tốt nghiệp được?
Chất nhận E mạnh nhất.
Hả? Cái gì?
Vâng.
Thêm cả đồng nữa đủ bộ.
Chất oxy. Đầu.
Đã bao giờ nghe KMN4 chưa? KMN4 là gì?
Chất tạo oxy. Phân hủy ra oxy.
So, if you put potassium permanganate KMnO4 in an acidic solution like F2NO4, it becomes a very strong oxidative agent. It can burn water. It can burn paper. It can burn easily. Okay? In an acid solution. But if you put potassium permanganate in water at the neutral pH, it's already a strong oxidative agent. Bởi vì nó là chất oxy hóa rất là mạnh, cho nên người ta ngày xưa ấy, cái thời mà nó chưa có cái đồ để rửa tay ấy, mà bị dịch bệnh nhiều ấy, của những năm 60 ấy, là người ta trước khi ăn đồ là người ta nhúng đồ của người ta vào cái dung dịch KMNO4 đấy, xong rồi rửa lại thôi, có gì để mà nhăn. Và những cái người mà người ta kể lại là ngày xưa bố mẹ người ta nhúng đồ ăn vào ấy, bây giờ họ toàn 80-90 tuổi, rất là khỏe, không sao cả, đúng không? Trời ơi. Okay, so for example, if you take pencil, you take graphite, you put in solution of potassium permanganate in the acidic solution, you heat it up, you will have graphite, which will be oxidized to get graphite oxide, and the graphite oxide have high solubility in water. Okay? Tất cả những thanh niên nào vừa nói nhầm chất oxy hóa là vàng bạc đồng, nếu mà được 16 điểm hóa thì thầy tự động trừ đi 6 điểm. Lên phường mà hỏi.
Xuống. Xuống.
Okay. So for example, you do the oxidation. So you will have, for example, here you have OS group, COOS group, and all of these can make a higher polarity. Okay? Rồi. Bây giờ thầy hỏi nhé. Thầy muốn làm tăng cái độ tan của graphene. Tại vì cái này nó liên quan đến tiền, bây giờ mọi người đang làm. Tí nữa các bạn, nếu như mà các bạn ra khỏi phòng ấy, đến cái nhà gửi xe của nhà trường ấy, ra khỏi cái nhà gửi xe ấy, nhìn thấy có cái đèn cao áp đúng không? Trong cái đèn cao áp đấy nó có một cái loại dầu tản nhiệt. Tại vì khi mà cái đèn cao áp nó bật đấy thì nhiệt độ nó rất là nóng. Thế thì để mà nó đỡ bị hỏng các cái mạch điện ấy, thì người ta phải dùng một cái loại dầu tản nhiệt, tức là nó truyền nhiệt ra môi trường rất là nhanh, đúng không? Thì cái dầu tản nhiệt đấy nó được làm bởi graphene. Tại vì graphene có độ tản nhiệt rất là tốt. Graphene này được hòa tan ở trong cái dung môi, và cái dung môi đấy thì không độc, và dung môi không độc là nước, đúng không? Thế thì cái dầu tản nhiệt đấy là do giáo sư Phan Ngọc Minh ở GUS, là Học viện Khoa học Công nghệ, ngày xưa là phó chủ tịch Lâm, nhóm của giáo sư phát triển và dùng ở trong cái đèn cao áp bây giờ. Trong các đèn cao áp ở Việt Nam mà đi ở trên các đường cao tốc ấy, thì là họ dùng cái dầu tản nhiệt đấy, được chưa? Thế thì một trong những vấn đề là để mà làm được dầu tản nhiệt đấy, nếu muốn nó tản nhiệt tốt thì cái dầu đấy nó phải bền, đúng không? Bền kiểu theo nghĩa là nó không đóng cặn lại, đúng không? Mà muốn nó không đóng cặn lại thì nó có phải có độ hòa tan tốt, đúng không? Thế nhưng mà bây giờ nếu như mà các em oxy hóa như thế này thì những cái mạch và những cái liên kết pi nó bị cắt, đúng không? Đồng ý không? Thì chỗ nào mà liên kết pi bị cắt thì chỉ còn lại liên kết sigma, đúng không? Kiểu theo nghĩa hai thằng này nó đang nắm tay nhau, tự nhiên oxy hóa là nó không nắm tay nhau nữa, đúng chưa? Thì cũng như là cái cậu kia cậu vừa nói là cái mạch graphene lớn phải cắt nó ra, đúng chưa? Thì cái độ dẫn điện và dẫn nhiệt nó sẽ giảm đi, ok không? Thế bây giờ thầy mới đặt câu hỏi tiếp theo, câu hỏi cuối cùng là chi tiết. Nếu như bây giờ thầy không muốn thay đổi cái độ polarity của nước, thầy cũng không muốn oxy hóa graphene, thì làm thế nào thầy vẫn làm cho nó tan được vào nhau, đúng không? Hiểu ý không? Oxy hóa thì tan thì ok rồi, cắt nhỏ ra tan thì ok, thì thực ra cái cắt cái oxy hóa của này thì cách cắt nhỏ không kia nó giống nhau thôi, đúng chưa? Làm giảm cái conjugated, tức là độ liên hợp trong liên kết. Thế bây giờ làm thế nào? Làm nào? có làm được không? Không thì không thì thôi nghỉ việc để người khác làm.
Thầy dùng mối khác.
Thầy kể cho nghe có một cậu sinh viên của khoa hóa là thầy tốt nghiệp đi làm cho một công ty ở Việt Nam, công ty tên là Tesla nhưng không phải Tesla, tên là Tesla. Làm cho công ty của Việt Nam. Nó đi vào làm thì nó làm ở bộ phận AD, mà thế là nó rất là excited. Nó ngày xưa đi học thì toàn bị thầy Phong thầy mắng, giờ đến cơ quan sếp chiều lại, sếp cho mình ngồi một tầng để tập trung nghiên cứu. Tháng rưỡi sau nó bảo em lại tự do để thầy. Lý do là bởi vì sếp yêu cầu là đấy, bây giờ công ty thì đang nuôi tôm ở trong miền Trung ấy, ở trong Huế ấy, và nước tôm nó bị ô nhiễm nhiều lắm. Mà khi mà nước tôm nó bẩn ấy, tôm nó là cái giống rất là dễ bị bệnh, đúng không? Tôm mà đợi đến khoảng vài chục ngày nữa bắt đầu thu hoạch thì bắt đầu chân lăn ra nó chết thì công ty phá sản. Thế bây giờ sếp cũng mới hỏi là đấy, cậu cử nhân hóa trường USTH nghe vẻ được đấy, là xử lý nước tôm cả trong một tháng phải làm, đúng không? Một tháng nó mới mang lên cái proposal. Thế nó về nó kể chuyện mày mà mang cái proposal đấy thì thầy không những thầy đuổi việc mày, thầy đánh mày một trận. Nó đề nghị là, biết là nó đề nghị gì không? Nó đề nghị là dùng graphene để xử lý nước tôm. Mẹ ơi, graphene là nano material, được một tí này mà nó vứt xuống đầm tôm của người ta bao nhiêu hecta thì được bao nhiêu, đúng không? Ông sếp ông sợ quá, ông bảo công ty chưa dùng được advanced technology như của em, thôi em nghỉ đi. Đó, đấy những cái thực tế mà các em bắt gặp ở trong công việc nó là như thế. Thầy không tưởng tượng nữa nhá, nó là một thanh niên thật ở trường này luôn, vừa tốt nghiệp trường này luôn. Đó. Thế thầy mới đề nghị nó như này. Hôm nay thầy đề nghị luôn nhá, nghe nó rõ nào. Nếu mà sau này đi làm mà tất cả liên quan đến gì về material science, liên quan đến chemistry, nếu mà sếp giao cho việc mà chưa xử lý được thì biết làm gì không? Cái này khó, anh để em về nghĩ đã. Khó lắm, để em về nghĩ đã. Xong inbox cho thầy. Thầy nói thật. Cái quan trọng là mình phải biết tìm cái người mình hỏi, chứ đừng có tự tin vào hỏi ông Google rồi phán một câu xong là chết đấy. Cái này khó anh ạ. Để em về em nghĩ. Hỏi thầy Phong luôn. Nếu mà thầy Phong mà thầy cũng không biết, thế thì thầy phải tìm được người biết, thầy trả lời cho em cái. Được chưa? Thế xong đấy thì ta chia 50-50. Đúng không?
Tiền lương.
Làm ăn thế nó mới lâu dài được chứ.
Cái 50 lâu dài đấy.
Đồng ý không? Tức là nếu mà muốn làm free thì được một lần, từ lần sau inbox thầy không trả lời nữa, đúng không? Nếu mà làm 20-80, tức là em lấy 80%, thầy lấy 20%, thì lúc nào hứng thì thầy trả lời, ít tiền thầy trả lời, đúng không? 40-60 thì cũng được. Nếu mà 50-50 thì cứ inbox là thầy trả lời luôn. Đúng không? Bọn em phải chạy deadline, thầy phải chạy deadline chứ. Ok, nhá, nhớ, thầy nói thật đấy. Không phải cái chuyện 50-50 là thầy đùa, nhưng mà chuyện thật là khi mà các em bắt đầu đi làm ấy, cái lúc mà các em cần accumulate kinh nghiệm ấy, thì đừng có quyết định cái gì vội. Nếu mà sếp nói thì phải, nếu mà sếp đưa ra, tất nhiên ông bảo tính số môn cho anh cái, phải bảo em cái này khó để em về nghĩ nó bảo chết, đúng không? Nhưng mà ví dụ những cái gì mà nó mang tính creation một tí, innovation một tí, nghĩ ở vò đầu vứt tai nghĩ cái này khó đấy. Còn để em về em nghĩ. Đó. Hoặc là khôn nữa thì ma anh tí nữa, biết từ ma anh đúng không? Khôn vặt một tí nữa là công ty mà để mà ngồi nghĩ cái này mà anh cho em ngồi trong công ty này không làm được đâu. Cho em ra hai đời coffee hay là Starbucks em ngồi. Thế ra đấy là cứ inbox trong phòng đó. Không inbox. Tất nhiên là sau khoảng 12 tháng, 12 tháng, 24 tháng bọn em trở thành expert trong đấy thì đã đi tâm phong ra không cần nhờ nữa, đúng không? Lúc đấy mà lâu lâu thầy Phong hỏi thế tình hình công việc như nào thì không trả lời nữa. Đó. Tại vì sau 24 tháng mà bố vẫn còn hỏi ấy, mà bố làm free mà 24 tháng sau bố hỏi, chắc bố lại chuẩn bị mời về chia sẻ cho sinh viên hay là alumni thôi mà, chứ có cái việc gì đâu. Okay, so how can we do? One of the possibility is that you know there's some polymer. The polymer can disperse very well in water. Okay, so the idea is that. So sorry, we have to go. Okay. Look, if this graphene, okay, what you can do is that you cover this graphene with one polymer. Okay. So it looks like the graphene will be inside the polymer. And if the polymer dissolves very well in water, then the whole system will disperse in water. Okay? So that's something people is doing. For example, Dr. Đức Anh in my department work quite a lot on this kind of thing. Okay? The second question can be also the final question, is that how the functionalization influence on the graphene electrical conductivity. For sure that you cut the double bond, the electrical conductivity will decrease, right? Okay, now 1 hour 40 minutes we will talk about the molecular orbital. So we have learned already about the valence bond theory and hybrid orbital, but they are indicated to describe the excited state of molecule. They are all very good to explain the bonding of the molecule at the ground state. Okay? You understand what I mean? But, for example, when you have a molecule, if you see the color of molecule, that is because the molecule can absorb the photon, right? You remember that, right? If it absorbs the red light, you will see the green color and the invert. So, if one compound have color, so it means it can absorb photon. But it absorb photon, it means it absorb photon energy. And by the law of energy conservation, you absorb energy, you should move to the higher energy level, right? So for the moment, all the valence bond theory, all the hybrid orbital that we described, can help us to understand the bonding. But none of them can help us to understand why one compound can absorb photon energy, excite, and see the color. Okay? So how we can express, how we can explain this kind of excitation? That means the electron transfer from the ground state to the excited state. So to explain it, people develop what we call the molecular orbital theory. What we learned until today is atomic orbital. That means the orbital of the atom. That means the electron distribution around the nucleus of one atom. Now you will not consider one atom anymore, you consider all atoms in one molecule. And we will see how the electron distribute, not only surround one atom, but in all these molecules by using what we call the molecular orbital. So here is a concept. If you have a two orbital S, if you have two atoms with two orbital S, you make the bonding. 1 plus 1 equal to 2. It will generate two molecular orbitals. From two atomic orbitals, it will make two molecular orbitals. The difference is following. Two atomic orbitals will have the same energy, right? However, when you make two molecular orbitals, you will have one at a lower energy and one at higher energy. Okay? Of course, you take the average, it's still the same energy compared with the initial state. But you will have one molecular orbital which have lower energy and one molecular orbital with higher energy. In terms of electron distribution in the two orbitals. The bonding molecular orbital, that means the orbital will decide the bonding, have a lower energy level, and the electron density will look like in between the two nuclei. Okay? And when electron look like in between the two nuclei, that means you create the bond. So that's also why we call this molecular orbital as the bonding molecular orbital. Because if electron is look like here, it will create the bonding. It will have another orbital we call the anti-bonding. Again, the bonding orbital, where the electron will not stand in between the two nuclei, but in two different sides. If you want to create the bonding, that means the electron should be in between. Now electron will not, but stand in the two heat. That means you separate the bond, you cut the bond. So what I mean? It means that if you have an electron here, in this orbital, at a lower energy level, the system will gain in terms of energy, right? That means the creation of molecular orbital will help you to economize, to save energy, to lower down the potential. And you know that all the system lower down the potential will be stabilized. That means the bonding will create. So if you have an electron here, you make the bond. So that's why you have a bonding molecular orbital. Now, if this electron here receives energy, it will excite to this orbital. Okay? And at this orbital, at higher energy level, electron will not look like in between the two nuclei, but in two different atoms. That means you break the bond. It means that if you have an electron here, you send energy, it excites, you have from one bonding to break the bond. It means the energy you just send have to cleavage to cut the bond. Okay? It also means if you want to do a chemical reaction, you should put energy to make electron from here excite to here. Is it correct? Because when electron move to here, it will break the bond. Because the chemical reaction representing the breaking of one bonding and create a new bond. Right? So by the concept, here you have anti-bonding molecular orbital. That means when you put electron in this orbital, it will again the bond. And you have bonding molecular orbital. So here you have one atom of S of hydrogen in the orbital S. You have one electron. You have another atom with a second electron. Now you put together to make molecule A2. Okay? So when you put together, the two electrons will belong to both. Okay? So the two electrons will put from the lower energy to up. So they will put in the bonding molecular orbital at a lower energy. So you have orbital bonding with two electrons here. So you can see here that when you have two atoms, you put the bond in the electron in the molecular bonding orbital. That means you gain in terms of energy. So the bonding will happen. Okay? So in this case, you will have hydrogen can make a bond. So the message, two electrons occupy the lower energy bonding orbital with lower energy than the isolated atom. So in general, the system gain in terms of energy, save in terms of energy, economy the energy, right? Now, if you take the case of helium, X orbital helium will have two electrons. So now imagine that you consider two atom helium. You will have 2 plus 2 equal to 4 electrons. So you have one orbital S, one orbital S, it will generate one bonding orbital and one anti-bonding orbital. That is general, right? So now you put 4 electrons in the 2 orbitals. First, you put 2 electrons here, and the second, you put 2 electrons here. So now you have 2 electrons occupy the lower energy level, and 2 electrons you occupy at the higher energy level. So in total, the net energy will be the same as before you make the bonding. Right? So it means that in the scheme of helium, if you put 4 electrons in this case, you will not gain any energy. You will not save any energy. But you lost the freedom. Okay? If you make the bonding, that means you lost the freedom. You will not gain anything, you lost the freedom. So basically you refer to not produce the bonding. Okay? So we have the concept of the bond order. Bond order means the number of electrons in the bonding molecular orbital. Minus the number of electrons in the anti-bonding molecular orbital, you divide by 2. Because each bond corresponding with 2 electrons. So if you take the difference of the electron between the bonding and anti-bonding orbital, you divide by 2, you have the bond order. That means the number of bond. If you have the bond order equal to 1, that means you have a sigma bond. If the bond order is equal to 2, that means you have a double bond. 1 sigma and 1 p bond. Okay? But by this concept, it will have also the bond order 0.5 and also 1.5. Okay? So, thầy biết là chỗ này rất là khó hiểu. Nhé. Để hiểu thì đơn giản như thế này. Bây giờ hai ông muốn share phòng với nhau đúng không? Mỗi ông bố mẹ cho tháng mấy triệu?
10 triệu.
Vãi.
10 triệu thì khỏi share phòng.
Đi mẹ.
10 triệu thì thuê nhà nữa.
Đây giả sử. Rồi. Mỗi ông một tháng bố mẹ cho 3 triệu đi.
3 triệu.
Ok. Đó, một tháng 3 triệu. Hai bạn rất thân với nhau. Còn thuê 2 phòng. Mỗi phòng 1,5 triệu. Cuối tháng ông nào cũng hết tiền. Đó. Không có party gì cả, không lên hồ gươm được. Ok. Nhưng được cái không có tiền nhưng được cái tự do. Đồng ý không? Nếu như bây giờ hai ông share phòng, hai ông sẽ có tổng cộng không phải là 3 triệu nữa mà 6 triệu đúng không? Bây giờ phòng nó chỉ có 1,5 triệu thôi. Đó. Hai tên ăn uống vẫn hết 3 triệu bình thường, hoặc là có thể nấu cơm giảm xuống tí nữa, còn 2 triệu. Thế là tiêu hai bên tiêu hết 3,5 triệu, đúng không? Thế là còn 2,5 triệu tiết kiệm được. Và 2,5 triệu thì cuối tháng đi xem đi party vân, hoặc là đóng tiền đi lại. Thế thì bây giờ hai ông này sẽ chấp nhận chia phòng nếu như ông muốn tiết kiệm được tiền, đúng không? Bởi vì khi mà xe phòng đó thì ông mới mất cái gì tự do, đúng không? Thằng này nó ngáy là kia phải chịu. Hoặc là lâu lâu nó chơi game thì muộn thì cũng phải chịu, tức là mất tự do. Đúng chưa? Và trong khi đó con người ta thì muốn tự do nhiều hơn là bị mất tự do. Thế nhưng mà mình chấp nhận mất tự do, mình chấp nhận xe phòng với ông này thì sẽ được cái gì đấy? Và được cái gì đấy ở đây là tiền, tiết kiệm được tiền, đúng không? Còn hai ông này xe phòng mất tự do rồi, vẫn chịu nó ngáy, vẫn chơi điện tử, nhưng đến cuối tháng vẫn hết 6 triệu. Thì tôi thấy là xe làm gì, đúng không? Của nhà dân sống. Đấy, thì cái concept bonding ở trong molecular orbital là như thế. Tức là bây giờ nó để chung electron lại tạo thành bonding, đúng không? Nhưng mà nếu mà để electron làm sao đấy mà vào những cái bonding orbital nó có năng lượng thấp hơn, theo nghĩa là cuối tháng nó tiết kiệm được năng lượng, thì cái bonding đấy là bonding bền, có sẽ tạo được bonding. Tiết kiệm được càng nhiều, tức là sự khác nhau giữa electron ở bonding và electron non bonding, anti-bonding càng lớn, tiết kiệm được càng nhiều, thì cái mối quan hệ càng lớn, cái bond order càng lớn, đúng không? Thế nhưng mà chấp nhận mất tự do mà trả được lợi cái gì về năng lượng cả, trả nó được lợi cái gì về tiền tiết kiệm cả hạn, thì sẽ không có bonding nào cả, bond order nó sẽ bằng không. Thấy không? Dễ hiểu chưa? Có dễ hiểu không? Giải thích thế không hiểu thì chịu. Okay? So here you can see that the bond order equal to 1, right? And here the bond order will be 0. That means there are no bond. So the same you can see that for the lithium here, lithium 2 molecule, you will have this case. The barium will be 0 bond order. So bond order equal to 1, and here bond order equal to 0. The two electrons will occupy the lower energy bonding with the lower energy than the isolated one. So the molecule hydrogen, because it's lower energy, it will be more stable than hydrogen atom. Okay? So now about the orbital S. So if you consider about the orbital B, you have the same. Two orbital B, you will have one orbital B, we see the bonding, one orbital B anti-bonding. You see that the anti-bonding, the electron will not occupy between the two nuclei. Okay? So here you have the diagram where you have the orbital S, atomic orbital S, and here you have a molecular orbital S, and here you have a molecular orbital B. So you see that 1 plus 1 equal to 2, you will have 1 orbital bonding, 1 anti-bonding, 3 plus 1 equal to 6, you have 3 bonding and 3 anti-bonding. Now you put all the electrons together and they fill from the bottom to up. Okay, so you will have the electron configuration of the molecule. When you have the sp interaction, normally the orbital s will at a lower energy, but when you have an sp, for example, in the case of very early element, boron, carbon, and nitrogen, the orbital b will go to the higher energy level. So, what I request from you guys is understand the concept, but not remembering the diagram, because remember is not useful if you want. But understanding the concept, so when I ask the question about this molecular orbital diagram, you guys will be provide the diagram. Okay? You don't need to remember, but you will be asked by understanding the concept. Okay? So here you have the level, when you have the sp interaction, so you see that the sigma become higher energy, right? So you have this change in the level. Okay, so you have two systems. With the system for the oxygen, you will have this, and for the system with before nitrogen, you will have this. I mentioned you will not need to remember. So about the this property is quite easy. I mentioned already. So diamagnetic substance is substance where you have all the electrons are paired, right? Paramagnetic is substance that you have at least one single electron. So it's quite easy to understand. So, for example, here you have a lithium, all the electrons are paired, so you have diamagnetic. Here you have no bonding, so you don't care. Here you have two single electrons, so you have paramagnetic. Here you have two pair electrons, so you have diamagnetic, and here you have diamagnetic species. Okay. So how about oxygen? So oxygen, you have single electrons, so oxygen is paramagnetic, right? Okay? Is it correct? Now, important. You see that oxygen is paramagnetic and nitrogen is diamagnetic. All the electrons are paired. Okay? That is a reason why oxygen and nitrogen will not react. Okay? Because if the two compounds want to react, they should have the same diamagnetic or paramagnetic property. Okay? So now, another understanding is like following. If you take a compound like methane, CH4, okay? Do you think that CH4 is paramagnetic or diamagnetic? CH4. So in CH4, you have 4 sigma bond, right? And all sigma bond, you will have one pair of electrons. So basically, the molecule CH4 is diamagnetic. So it means that you cannot burn CH4 with oxygen. There is no reaction between oxygen and CH4. Right? Basically, if you keep at room temperature, here is the trick. If you keep at the room temperature, you open one cylinder of CH4 here and one open cylinder of oxygen here. The two gas will mix in the room, and then no reaction, then no burn, no explosion. However, if you take the fire, you turn on the fire, the reaction will happen, and you will have exposure. Is it correct? So that's why when the worker want to burn CH4 or C2A2, they need to get a first flame, right? Get the fighter to eliminate the first flame. Then the reaction will happen. Why? Because look at the CH4. Sorry. Look at the oxygen here, right? So now, when you heat it up, you turn on the fighter. Okay? You get the first flame. Then you will get excitation. The electron here will move to the orbital. So from the two individual unpaired electron, they will pair. So from the paramagnetic, it becomes diamagnetic. And when it becomes diamagnetic, it will react with CH4. And when it reacts with CH4, the reaction is exothermic. And because the reaction is exothermic, that means it really heat. It will excite again another oxygen. And when excite again other oxygen, the reaction will keep continue. Okay? So that's why when you want to stop the flame, you have to remove oxygen. Otherwise, there's nowhere to remove. You remove the oxygen, so there's no more oxygen to get excited. So you see what I mean? So if you take two cylinders at room temperature without excitation, they will stand for life. There's no problem. They will make a homogeneous mixture. But when you excited it by either flame or by electrical excitation, the reaction will react and it will relieve a lot of heat. Okay? So, for the heteronuclear diatomic molecule, so you have the same diagram, or you have nitrogen, oxygen, so you put all electrons together. So here again you see that NO have one single electron, right? And because NO have one single electron, so you have a dimer. That means two molecules NO will bond together to make a nitrogen-nitrogen bond, right? So CO molecule, you see? So here you have all the CO all electrons are back. Okay? So you know this famous reaction, right?
Yes.
So in your blood, you have hemoglobin. Okay? And then this is one iron complex. So when you have a molecule of oxygen, the molecule of oxygen will stand here, so it carry oxygen. Okay? However, when you have CO, the bonding between CO with this iron is 1,000 times stronger than the bonding between oxygen and the same hemoglobin. So that's why when you get poisoned by CO, the body die because there's no more oxygen. Okay? So the blood cannot carry oxygen anymore. And it will be about like 1,000 times stronger. So in this temperature, very cold, some provinces, they still use the carbon, the charcoal to burn it. And when you burn this, with the condition of low oxygen density, it will generate a lot of CO. And the CO can be toxic. Okay? So when people get poisoned by CO, how can we rescue? You have to put a lot of oxygen. If you know this, you take a big cylinder of oxygen, you put the high pressure of oxygen. So when you increase the concentration of oxygen, so then you remove the CO. You get what I mean? But if you don't increase the concentration of oxygen, the CO will be 1,000 times stronger, so there's no oxygen carry, the people will die. Okay? If you take an adult and then a baby, the guy like you guy will be poisoned faster by CO than the baby. So like one baby or mother sleeping in the same room, when they get poisoned by CO, the mother died, but the baby still survives. Because the breathing system of the baby have not yet well developed. So the requirement of oxygen is much less. Okay, so we have learned the key point about the molecular geometry, geometry of polarity, valence bond theory, hybridization, molecular orbital, and so on. Okay? So here we have some pointer for you guys because that is coming. Some of you may ask question, why do we learn about geometry of molecule? What could be the greenhouse effect? And why all the time when we talk about the greenhouse effect, we talk about CO2, right? A lot of people say that you need to balancing the CO2 emission to cut the temperature increasing, global change, global warming, climate change, and so on. But is there other greenhouse gas effect why we all the time focus about CO2? So first, what is greenhouse gas effect? Okay, and I try to explain why we need to learn about geometry. So here you have two molecules. One CO2, right? You know that in terms of geometry, which is linear compound. The second compound is water, which is a band geometry, right? And you have the other compound CFC, C, the first C for the chloride, second C for the fluoride, and the last C for carbon. Right? So you have CF2Cl2. This gas is being used to in antifreeze at home to cool down the temperature. Okay? So when this gas leak to the atmosphere, it becomes also very dangerous gas for the greenhouse effect. Why it does? So this is the greenhouse effect. Basically, the sunlight will reach the surface of the earth, okay? And then you will have some radiated energy. So when it's radiated back, that means emit back the energy. In the atmosphere, you have some molecule that can absorb the energy, okay? By moving from the ground state to excited state. Accept the energy. That is during the daytime. In the nighttime, the gas already accept energy will emit back to become back to the ground state. Okay? So normally in the nighttime, the temperature on the planet will cool down, but because the energy irradiated from the atmosphere back to the surface of the planet, so the temperature of the planet increase. Okay? So it means that in the air, if you have more greenhouse gas, that means more gas that can absorb the energy emitted from the surface and then send back to the surface of the earth, the temperature will increase, the warming will be much more significant, right? Where the oxygen can absorb the energy and emit it back? No. Where the nitrogen can absorb energy and emit it back? No. But why CO2 can absorb energy and emit it back to make the temperature increase? Because you learned this one already, right? You learned this diagram. So if you have this ground state, that means, if you remember, the bonding between the hydrogen and hydrogen, right? The bond distance is here because it is a lower energy level. But when you move to this position, that means the bonding is still stable, but it gets longer. So that means normally you are at this distance, you put energy, the red line, the infrared line, it will get excited, so to this position. Then when it's removed back, it will emit energy, so it's warm up the surface earth temperature. Okay? So, by the law of selection, here you have a CO2 and you have a different vibration mode. Let's say you have this compound, the carbon will be in the middle, two oxygen will go like this, okay? And you see that in this vibration, the molecular moment, the dipole moment will be 0 all the time, okay? you get longer or shorter, the moment will be 0. If you do by this way, and the oxygen go far, that means the dipole moment will change from 0 to different. Here, the moment will change as well. So here also, you change the dipole moment. So by the selection rule, all the vibration with different moment, with the moment difference than 0, will be allowed. That means this vibration will be not allowed by the excitation. But all of these vibrations will allow. That means the molecule of CO2 have a several chance to absorb the infrared energy and then re-emit temperature back to the surface. Okay? The same for the molecule of water. Molecule of water can vibrate, and all the time the vibration of molecule of water will be different than 0. That means the molecule of water can absorb energy and emit energy. So water also cause the warming of the surface energy on the planet. By understanding that, you may ask question, but why all the time we talk about CO2, we don't talk about the water? Is it correct? All the vibration with dipole moment difference than 0 are allowed. And all these vibration will cause the absorption of the infrared energy and emission of infrared energy, so make the temperature increase. That means both water vapor and the CO2 are the agent cause the temperature increasing. But why all the time we talk about CO2 but not water? Huh? We should be fair, right? Or just because we don't like CO2, so we talk about CO2? No. What it could be the reason? So, you don't know, right? So, first question, does water absorb infrared photon? Yes, because the dipole moment difference than 0. Is water a greenhouse gas effect? Yes. But why do we talk only about CO2 but not water? Huh? So here is the reason. You see that's CO2 in atmosphere and annual emission. So basically you will see that here you have a CO2 in atmosphere. Okay? And here you have CO2 emission. That means when you emit CO2, the CO2 will come to the atmosphere. Huh? The reason is that the solubility of CO2 in water is very low. CO2 is non-polar, water is polar. So even you have a very big surface of the planet covered by the sea, a lot of water, but the solubility of CO2 is very low because of the difference between the polarity. So all the CO2 you emit, it will not dissolve in the water, but it will go to the atmosphere. And that will contribute to warm the temperature. How about water? So of course you will have very high solubility of water in water, right? Is it correct? So here you have the capability to retain the water moisture in the gas. Because the greenhouse gas is only considered for the water vapor, not water molecule, liquid, right? So it means that only the water vapor stand in the atmosphere will be contributing to the increasing the temperature. But the problem is that the water dissolves very well in water. And water stands quite little in the air. So all the time you have, when you have water vapor increase in the air, the wind precipitate and you have the raining, so it becomes liquid again. So basically even the vibration of water contribute to warm the temperature, but the amount of water in the atmosphere is stable, low. Okay? So what could be the consequence? Now, if you don't cut the CO2 emission, okay? You don't cut CO2 emission, you will have the greenhouse effect. The temperature on our planet will increase. And when the temperature on our planet increase, that means you will have more water from the liquid to become vapor. And when you have more water from the liquid to the vapor, that means the water contribution to increasing the temperature will be more significant. That means the temperature increase more, then you have more water come to the vapor and you have more temperature increase. So you start to come to a kind of catalytic process where you cannot end anymore. Okay? So CO2 is the bad guy, but after that, it will also start the catalytic process where water becomes more significant. Right? Okay, climate change maybe tomorrow, but final exam are coming very soon. Okay? So keep calm and destroy all the final exam. Thank you.
Destroy 10 points.
Bye bye.
Có đi khỏi bánh.
Thứ ba tuần trước các em có đi học không? Thứ ba tuần trước em không đi học à?
Không.
Thứ ba tuần trước em nghỉ có việc gì ạ?
Việc em bận.
Em bận à? Ok. Thứ ba tuần trước em không đi học, tiết Linear luôn.
Đó.
Linear cuối.